This lesson deals with the addition rule and multiplication rule for probabilities. So first of all, just a definition here, a compound event is when we have an event with two or more simple events, and we might look at a compound event where we put or, and it's possibility we'll look at a compound event with an and, because sometimes we're happy with either the first outcome or the second, fine if there are both, and sometimes it's only going to work if they both happen at the same time. So looking specifically at our rules then, we have an addition rule, and this addition rule could happen in two different forms, but the one you're looking at right now is the most critical form. Now when we say or, it does mean it's inclusive, and I mentioned that on the previous one. It means it's okay if it's A, it's fine if it's B, it's fine if it's both of them. But the reason we have subtraction on there is so that we don't end up counting anything twice. So let's look then at this example here. If you're going to draw a card from a standard deck, the standard deck has 52 cards in it. And again, if you're not real familiar with it, it's used frequently for probability illustrations. So you might want to look at a sample space for a deck of cards if you're not familiar. But out of the deck of cards, half of them are red. But rather than put 1/2 here, I'm going to talk about the number of cards, because why reduce it? When we deal with fractions, it's easier to have a common denominator. So in a deck of cards, if we're interested in getting a red or a queen, we can do the probability of red plus the probability of queen minus the probability we get a red queen. There are half of the cards, or 26 out of the 52 cards, are red. 4 of the 52 cards are queens. But 2 of the cards in the deck are both red and queen, and so what's happened is that those 2 we have to subtract off, because we counted the red queens over here with the reds, we counted the red queens again with the queens, and so we subtract. And it might say, well, why subtract? I just wouldn't have counted them both times. You're going to run across some situations where it's too hard to just count them. And so this is often an easier way to do it. But when we have a common denominator, then you could just use your numerators and go straight across. 26 plus 4 is 30. 30 minus 2 is 28. Now this does reduce, but we generally don't need to reduce, because what they're going to want you to enter is the decimal almost all the time. So I can just pick up my calculator, 28 divided by 52. Do make sure when you're doing your homework, you look closely at what they want you to round this to. And so that number is, to 2 decimal places, approximately 0.54. Approximately 0.54. It makes sense that it's a little bit more than half, since half the cards are red and there's a couple of queens that aren't red. It's going to increase it a little bit more than half. Let's look at this again. This is also an example. You may have some information like this. Whenever you see a chart, I'm going to tip down here, you're probably going to want to add a row and a column to it. This chart may look very familiar if you watched the last video. It's the same chart that we had in the last one, but there are no totals given. And since to find probability, we have to know the total, we're going to add both the columns and the rows. So 8 plus 14 is 22. 44 plus 12 is 56. 8 plus 44 is 52. And 14 plus 12 is 26. And then whether or not you are adding horizontally or vertically, those are going to add up to the same thing, and we get 78. So we can use 78 as our denominator. So if we're going to do the probability that the test indicated no lie, or that they actually did not lie, we're going to follow our formula from the previous thing. First of all, what is the probability the first thing happened? The probability the test indicated no lie. Well, that's on a row. The test indicated no lie is on this row. So there are 26. So it gives me 26 out of 78 for the probability the test indicated no lie. Now it says or did not lie. So the probability they did not lie is on the column. And that gives me 22 out of 78. However, you can see that both of those lines crossed that number 14, and that's the number then that we've counted twice, because we have to subtract off when these both happen. When did it indicate no lie and they did not lie? That's right here, so I need to subtract off that 14 out of 78 because it got counted both directions, and we don't want to double count that. So then the 26 plus 22, 26 plus 22 is 48, and 48 minus 14 is 34. So now I'm probably going to need a decimal, and again, I just can't say it enough. Make sure you look closely at what they want you to round to. 34 out of 78. So approximately 0.44. Approximately 0.44. The fraction is exact, but when I don't have an exact decimal, that's an approximation then. All right, so we've done a couple of those then. If you are trying to do the or, you've got to add, and then don't forget to subtract out that overlap if they do overlap. Now, it's possible that they don't overlap at all. Some events, there's no overlap. They're totally disjoint, which is the same thing as mutually exclusive. They simply cannot occur at the same time. It's one or the other. And so if you have disjoint events, you don't have to do the subtraction part. So while I say over here, you will have to use this formula, in all honesty, you can just use this formula for all of those addition rules, but sometimes this would simply become a 0 drawing a 2 or a queen. The probability of drawing a 2 or a queen. Well, the probability of drawing a 2, there are 4 of those in the deck of 52, and there are 4 queens in the deck of 52. There is no need to subtract because the probability of getting a 2 and a queen is 0. So even if you used the other formula where it had subtraction, you would be subtracting off 0, and it would make no difference. So 4 out of 52 plus 4 out of 52 is 8 out of 52. Calculator time, 8 divided by 52. And we have approximately 15% or 0.15. Now those are called disjoint or mutually exclusive events because they cannot happen at once. If they can't happen at once, the and part becomes 0, so you just don't need it. Moving to the multiplication rule. If you're looking at an and, then really what you're looking at is what is the probability that this first part occurs in the first trial and the second one occurs in the second trial. So the probability the first one happens and the second one happens. Now, the idea that B has to occur after A already did is this sort of symbolism. And if we read this from left to right, I know it doesn't look like it says all this, but we generally read that the probability of B given A. Now, the probability of B given A means what is the probability of B happening after A already happened? So not at the same time, but that after A already happened. And that requires multiplication. Sometimes I think the formula looks a little bit harder than actually applying it is. So suppose that you're going to draw 2 cards without replacement. We're going to talk about that phrase on the next page, but that's an important phrase. But without replacement. If you don't replace it, what is the probability you get a 2 and a queen? Well, we know they're not going to happen at once. So we're talking about drawing 2 cards, not 1 card. This means what is the probability you get a 2 on your first draw, and then you get a queen after you draw the 2? because they certainly didn't happen at once. Now, the probability of getting a 2 on the first card, well, there are 4 2s, and there are 52 cards in the deck. But when we go to draw the queen, we didn't put the 2 back. It says without replacement. So there are no longer 52 cards in the deck. There's only 51 cards in the deck now, even though there are still 4 queens. We have 4 out of 52 times 4 over 51. The moment you're multiplying big numbers like this, you definitely want your calculator, and we're going to use a decimal anyway. So 4 over 52 times 4 over 51. And let me just hit clear here. Alpha y equals, enter 4 over 52 times 4 over 51. And I get 4 over 663, which is exactly right, and they're not going to want it in a fraction. They're going to tell you to enter an integer, which is a whole number, or a decimal. And so I need to change this to a decimal, so I can just divide 4 divided by 663. That's probably about as easy as any way to go about it. However, you could take that and hit math and then choose this one, number 2, that says go to a decimal and enter. It gives you the same thing. So if you'd rather have your calculator just say change this to a decimal, you can. But at any rate then, the chances of you drawing a queen right after you draw a 2 are really small. That's approximately 0.01. A 1 out of 100 chance that that's going to happen. Now, I have a note down here. This is different than drawing a 2 and returning it. If you're drawing a 2 and returning it, then your denominator doesn't change. And again, this is the same thing we had just a minute ago. Without replacement, the probability of drawing the 2 and then drawing the queen. I used to tell my students all the time, you add for or, add for or, add for or. If you say that enough, that's how you'll know if you should add or multiply. Add for or. You multiply when it says and. Add for or. So when we look at this one, once again, what we just did on that previous thing was the probability of drawing a 2, 4 out of 52. If we don't put it back, then the probability of drawing the queen is 4 out of 51. As opposed to this one, where it says that it is with replacement, the probability of drawing the 2 is 4 out of 52. But then the probability of drawing the queen after we draw a 2, well, since we put the 2 back, it has absolutely no effect. It's the same as just drawing the queen was in the first place. So if it's dependent, you should expect denominators to change. And if it's independent, you won't. Add for or. When it says and, you're going to multiply. Add for or. There is something called a cumbersome calculations. It's just kind of a phrase that goes with it. And if you have independent events, you always treat them as independent. But if you have dependent events, it gets harder to do the calculations because of those denominators changing. And so when we have those denominators changing, and if you did several different events, one right after the other, and it changed every time, it just becomes a royal pain to change all those denominators. So if you are dealing with sampling without replacement, so we would expect the denominators to change without replacement. If your sample size is no more than 5% of the population, and by the way, again, population doesn't have to refer to people, it's no more than 5% of the entire group you're looking at, you can treat the selection as independent, even though it was really dependent. So here's an example down here. You've got 15,958,866 adults in a region. A polling organization selects 1,235 adults without replacement. That just means they're not going to pick the same adult to answer the same questions twice. That's very typical for a survey. We say that's without replacement because we don't ask the same people the question again. If the selections are dependent, because the chances of the first adult getting picked are 1 out of 15, blah, 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 6. But the chances of the second one getting picked it's out of a 5. And then even here, when we start looking at these results, you know, if you said, what are the chances that an adult says something? Then we start changing things. So anyway, the sample is less than 5% of the population. Because if you had, let's just round that off and say it was 16 million, then 5% of that population would be about 800,000. And our sample is so much smaller than that, so much smaller. So this is less than 5%, so we would treat it exactly like now. That sounds like I'm not giving you enough information to do the problems, but what's going to happen is you're going to have some homework questions that just give you something, and they'll say, can we treat this as if it's dependent? And so you just need to double check and say that it's, see if it's 5% or if it's less than 5%. Now we talked about this one on the last video, but it's the complement of an event. The complement of event is A bar, and it means all the outcomes in which A does not occur. But this comes up several times in this particular homework lesson also. So let me point out that if I did a little bit of good old algebra and I like brought that over to the other side, then the probability of not A plus the probability of A would equal 1. But this is an addition rule. If we have added here, you add for or. So that means that it was the probability of A complement or A. This could be written either direction. So the probability of A or, and I know I called that A bar and then I called it A complement, same thing. Okay, the complement of A is equal to 1. So they could ask you to subtract to apply it, but they might also ask you something like this. The probability of that something will happen or that it won't happen is equal to 1. And just be aware that they're going to ask you to use that for subtraction, or they may rearrange it in one of those forms. Okay? So right now, I know you've seen this on the last one, but I'm just going to tell you again, you have to read carefully. You need to read especially in this section for did they say with replacement or without replacement, because that changes how you do it. You have to pay attention to whether or not there's a very large population and your sample is less than 5% of that population. That can affect how you do it. Look closely for the word not, because if you're only looking at numbers and some big letters, you may miss that word not, but that totally changes which group you're talking about. Okay? Please get in touch if you have any questions. I'll be available.